Hello, good morning, everyone. So my name is Aaryan Dubey, and I'm going to present on Paper Club. The topic of today's paper is "Don't bet on luck alone, enhancing behavioral reproducibility of quality diverse solution on certain domains." It's an interesting paper, generally based on quality diverse algorithm and how we can improve the reproducibilities in the solution that this quality diverse algorithm produce. So let's just see what is this quality diverse algorithm. So quality diverse algorithms are generally designed to produce a collection of high performing solutions. Generally, idea is to maximize the diversity in the descriptor space. So now you must be wondering, what is descriptor space? So generally, just imagine you are producing different solutions, right? A, B, C, D, E, F, G, H. So this descriptor space is the space in a particular space or something like that, where you can find the difference between each solution. So let's just say a solution is A, B. So what's the difference between A and B? What's the difference between C and D? What's the difference between D and D? So that's a descriptor in this whole quality diverse algorithm. So they say that when we introduce a noise, the fitness is generally, you have a solution A, right? You're going to evaluate it, how it's going to perform in that environment. So that is known as the fitness. A fitness and a descriptor of the same solution can differ significantly from one evolution to another. I would give you an example, like if you run a random forest classifier with different random states, right? Random states 1, 2, 3, 4, 5. So if you run it for 2 times, 3 times, 4 times, every time you will get a little bit different solutions, a differently trained model, something like that, with the same data and all the hyperparameter are same. So one is that example of this whole thing. So it says that this simply means that when you introduce a noise fitness and descriptor of the same solution can differ significantly from one evolution to another, leading to an uncertainty in the estimation of the such values. This whole paper focus on how we can remove this uncertainty in such values. So let's dive into the introduction part of the paper. So generally they introduce ARIA, archive reproducibility improvement algorithm. They say that we can reproduce of the solution present in an archive. Archive is a set of different performing solutions that quality diverse algorithm produce or an evolutionary algorithm can produce. So generally, query approaches rely on evolution process, which is used to estimate the performance of the given solution. For each solution, evaluation also result in descriptor, which characterizes the novelty of that solution compared to another. The proper definition of descriptor that is defined in the paper. So let's move forward towards it. So it says that most QD algorithms are deterministic, right? Deterministic here means that evolution of a solution always returns the same result. However, realistically, if you test a robot or a model, right, there might be some noise or something like that in the environment that always disrupt the solution that you're going to produce. An environment cannot be same every single time until you are testing it in vacuum or something. Even there might be some introduction to some noise or etc. So it says that every time you test it in that particular environment, there might be something different and you will get different solutions. So it says that in realistically, there are many contexts and application in which uncertainty is present in the evaluation process. For example, in robotics, the measurement from sensors may be noisy. So similarly, that's the idea which I was explaining to you people right now. So it says that quality diverse setups where domain present uncertainty belongs to the uncertain quality diverse framework. It says that QD algorithms are not designed to take this uncertainty into algorithm. They may produce illusory archives with many solutions, performance, descriptor, or wrongly estimated and may exhibit high variance. So to have a high reproducibility solution, they need to have a low variance, good descriptor, and a performance estimation. So in this work, we introduce archive reproducibility improvement algorithm. So it's generally simple. It can be used to plug and play tool, a plug and play tool applicable to any set of solution, including solution returned by quality diverse and evolutionary strategy algorithm, as I explained earlier. So it uses two formulas. One is reproducibility improvement mechanism, and which is generally defined here, but I will explain it to later down in the paper, which uses the natural evolution strategies to decrease the descriptor variance of the solution and maximize the fitness. So yeah, this is generally the simple introduction of the whole algorithm that we are going to do. So let's start with evolutionary strategies. What is the evolutionary strategies they are talking about? So let's see. So yeah, evolutionary strategies. So in this work, they define evolutionary strategy optimization algorithm that is applicable to high dimensional problems. So say that they say that instead of optimizing directly an objective function, generally we all know about the objective function. It could be an F1 score, or I'm talking about the machine learning model perspective, or it could be anything right now. So say that instead of directly optimizing that objective function, they maximize the exception of that objective function on the Gaussian distribution, which means that the variable theta is a variable to optimize and the standard deviation is kept constant, right? So they optimize the mean and standard deviation is kept constant. So it is common for ES to use rank-based utility function instead of objective function. In that case, gradient used to update the parameters. Here they were updating parameters differently. But here, if they are using a rank-based utility function as an objective function type of thing, in that way, the gradient used to update the parameters can be expressed using this formula, where theta s is sampled from normal distribution. Generally, this is a random variable. We will see how we are going to use this particular formula further down into the algorithm. Just to remember, this is the particular formula. Now we go for the quality diverse algorithm. So quality diverse algorithm aim at finding the collection, also called archives. Just to remember this word archive, because we're going to use it a lot in the algorithm. So a collection of archive, a diverse high-performing solution to optimize the particular problem. Unlike common evolutionary algorithm, QD algorithm consider that solution is not only assigned to fitness, but also descriptor, which used to measure their novelty. So, and we have this discussion in the past, right? When we are making the EFS, right? How novel is the creatures that we are producing, even when we are working with HPR? How novel is that particular creature? Is how many novel creatures are you producing? How that, but so yeah, generally that only. So common QD algorithms such as map-alike discretize this descriptor space into the grid. That means they take this descriptor and forms a grid out of it, like something like this. Archive of solution is there, and this particular, all the grids are known as the descriptor space. So where does this solution, like solution A, solution B, solution C, solution D, maybe solution E lies with solution A, something like that. So this grid is produced by map-alike algorithm. So we coming back here. Map-alike descriptor description in the cell. So at each iteration, they operate as follows. Solution are selected from archives and then modified via random variation, mutation, crossovers. Then their fitness and descriptor are evaluated, then added back to the archive. So more precisely, to add a solution to the archive, we first check which cell its descriptor belongs to, right? So in simple words, if you produce a solution, any solution, right, and the solution goes to this archives, maybe it could go to this purple one, it could go to yellow one, it will go to the aqua or teal one, something like that. So you produce a solution, you see which descriptor does it belongs to and add it to this particular grid. So it's just taking the solution and putting into a particular 2D map or 3D map or 3D graph type of thing, where you can put this descriptor. So this is the quality diverse algorithm. There are many variations to quality diverse algorithm, but generally we are going to deep dive more into the map-alike one because this paper generally uses that only. Now, uncertainty QD setting with descriptor, reproducibility, and axiom maximization, things like that. So quality diverse algorithm is done. So yeah, they say that reproducibility maximization. So say that distributors representation, how they are going to represent their distribution. So say that they say that the fitness and the descriptor values of a solution are represented as probability distribution, denoted as DF and DD respectively. So this accounts for the uncertainty in the values due to variation are called multiple evaluation. So it's simple. So they are going to maximize a particular function where this particular fi, that is our fitness function, and di is our descriptor function. So they are going to maximize this, the fitness function. They are going to minimize the descriptor, that is the variance in the descriptor. And last thing they're going to do is that, yeah, let me read it for you. Solution theta may lead to different fitness and descriptor. Theta can be represented to distribution as I explained, df and dd, considered expression. So we're going to maximize the expected fitness while expected descriptor value is this, belongs to the del ci. Additionally, we aim at minimizing the variance of the descriptor as I explained here. Components over descriptor dimension. In other words, we consider the following as a multi-objective problem. So in the end, they say that this particular problem, uncertainty QD setting with descriptor, reproducibility, maximization becomes a multi-objective problem where you have to solve 3 of this equation. We have to keep in mind this optimization problem, that was this df and dd, where we have to maximize df, becomes problem P1, which are we going to see in the latter part of the paper. This is the main algorithm array, right? Here we have set of genotype ES QD algorithm known as theta, number of gradient step n grad, number of samples per gradient ns, and standard deviation theta. Standard deviation, right? So, but before exploring this algorithm, I will deep dive into the reproducibility improvement phase and archive completion phase of this whole algorithm. I'm going to skip the related works. I don't think so there's anything more important here. But here, the method. We describe the repro array, a plug-and-play approach that can optimize a set of solutions to produce an archive of diverse, high-performing, and reproducibility solution. So in problem definition, we simply define it like this. They're going to take input, a set of solution, an archive set of solution QD, an optimized solution returned by an evolutionary strategies that we have seen earlier. Let me show you this. Evolutionary strategies return some solution. So that's going to take that. So first stage of this algorithm is reproducibility. Where it is, yeah. Reproducibility improvement phase. So what reproducibility improvement stage does is that it improves the reproducibility of the solution provided as input by using a reproducibility improvement mechanism. Simple, nothing else. So at the end, each solution takes an input step. We reevaluate it ns times and we calculate the mean descriptor. Mean descriptor, like I'll explain it to you, this whole reproducibility improvement. I have a code for it. So we calculate the mean descriptor observed from ns revolution of the same solution. Then we check which cell that descriptor belongs to and we put it into the mean descriptor. So as we know that reproducibility improvement mechanism to optimize for the performance and reproducibility of the solution with respect to cell tag. So let's see. Let's skip this. Let's look at this algorithm too. Reproducibility improvement algorithm. So initially it takes one values, genotype that is theta in one target cell, number of gradient n grad, and number of samples per gradient ns, and the standard deviation for sampling. It's going to initialize this particular genotype that we have taken. This genotype could be a creature, could be an optimization sample, even hyperparameters. I try to do it with hyperparameters just to see how it goes. So we initialize theta as theta in. So first we are going to initialize first loop, that is from number of how many gradient step we need to do. After that, we are going to see how many gradient samples that we are going to do right now. So 1 to S. Then we are going to take one particular sample from a Gaussian distribution. Your mean should be 0. And then it's going to calculate the stochastic evolution of the genotype, that is theta S, which is going to determine the new fitness and the new descriptor of this particular genotype solution. Using this equation, where ES comes from the sample, standard deviation is already defined, and theta is the particular value which we are going to give it here. Then we are going to use a rank-based unitil depending on the order of the objective function just to rank this whole scenario. There's a different equation for it, that is equation 1, that is defined above here. We're going to sample it, things like that. I'll explain it to what this particular example is. Then we're going to gradient estimate it, as we have seen in the evolutionary strategies. Here, this is the gradient estimate equation. Now we come back here. This is the gradient estimate equation. Then we're going to perform the gradient ascent, and then we'll have the return final genotype. So let me show you guys a code variant of this I was trying to do. Can you guys see my screen? Okay, yeah, let's see. So yeah. let's just say we have theta init is equal to 3, something like that. Theta, let me put it like this to be better here. Goes into a phase. No, better. Okay, yeah. Sorry for this, but yeah, let's go. Here we are. So yeah. So let's just say this is theta init. I just took a small samples of this just to test this how we can replicate it or use this algorithm. So this is theta init. Let's define it as 3, and we're going to initialize this that. C target 2, 4, any random value I keep it. This is x and y into a 2D space, something like that. Number of gradient, I thought it would be better to 3, and number of steps ns is equal to 3, right? As took standard deviation is 0.2, Right now, I'm using V, just bear with me. V is 0.03055. This is just a random value. Fitness is 879, descriptor is 3.2, 3.1, 3.3. Because I'm using 3 steps here right now, I use 3 descriptor because it's for this particular phase, it's going to run 3 times, right? So I use 3 descriptor, 3 fitness, because for every single thing, I need a fitness of descriptor here. Eventually, it will use a different function to calculate fitness and descriptor, but here, this is just a sample one. And this V equation is generally the sample that we're going to use here, this sample. So it's 0.03, 0.05, 0.02, something like that. So now if I run it for I in range number of grid, let's just say number of grid here is right now 1, right? So it will run 1 time. NS is right now 3. So first, what we're going to do is that we're going to find the score. Let me see. Temp n is equal to theta nn plus blah, blah, blah. So it's generally this equation that we are going to do here. I already told you people, like what is this particular sample and how we are taking it here. So right now we represent this sample. So V0, V1, V2, V0, V1, V2. So we are going to calculate temp n, that is theta nn plus standard deviation plus this particular equation. So we are going to calculate static evolution of the genotype. So we get temp n, that is generally our fitness. Then I'm going to calculate this rank-based gradient estimate. I already put the rank here as 1, 2, 3, something like that, because US represent the rank. So I just put it randomly 1, 2, 3. Then I calculate GE. GE comes around, I believe, 0.95 if I calculate it here. And after that is I add GE to our gradient descent step, that is 3 plus 0.95, generally comes 0.95. So this is generally step for this. Then I tried to calculate this whole reproducibility improvement algorithm in all, something like this. So it goes like number of gradient here is 3 and range is NS, something like that. So this particular step represents this algorithm. Theta AI is equal to NI N0 I Vj. And so I calculate V like that. Then temp n is generally our gradient stochastic evolution of genotype. Temp n represent that. So after that, I just calculate GE. Rank is almost same, 1, 2, 3. I didn't change the rank. Generally, this rank changes when we calculate a fitness or descriptor value by ourselves. So I calculate GE, things like that. And I try to replicate this whole algorithm. So if I run it, so initially, theta in it was 3. Let's try to run it again. It doesn't fail. And let's see, if I run it, it's something like this. So if every step of this 1 to NS is going to print theta in it. So it goes from 536, 6, 7, and 8.72 is the final. It's kind of going in a increasing direction, even if I put random uniform state as 0.02. So if I want to go in a different direction, I can emphasize more on the negative values and maybe it could reduce that. But that's my general idea of using it in place of hyperparameter optimization, how we can mutate it. But that's a simple idea how to use this reproducibility improvement algorithm. Generally, it's used in quality endeavors to reproduce the solutions in different aspect of things. But yeah, generally simple method. So let's move on towards a different phase of the algorithm. That is the archive completion phase. So at the end of the reproducibility improvement phase, there are still some cells in the grid that are not covered. So simply like this. This is the archive of solutions, right? So you produce different solutions, stuff like that. So maybe this cell, this particular cell is empty. Even all the solution that you produce, this particular cell is not filled. And maybe that particular cell contains the solution of the most optimized problem that you can have for this algorithm. So this archive reproducibility step, archive completion phase is generally says that only. For example, there's no input solution whose mean descriptor ends in a cell. Then this cell is still empty at the end of the previous phase. Therefore, after having improved reproducibility all initial solution, we have two complementary cells, where P exploration and P target. P exploration contains all the cells that have been used by the targets by reproducibility improvement so far. The purpose of this phase is to find the controllers populating the remaining cells to explore P target. To do that, we need to explore the remaining cells, P target, step by step, as depicted in the figure 1. We'll go back to the figure 1 soon. At each illustration step, we start by selecting a pair of cells CS and the C target. So if I go back here, You see, this is CS and this is C target. We are going to select the adjacent cell to the current cell. So I come back here, archive. Yep. We start by selecting a pair of cells CS and C target satisfying three conditions, where CS belong to P exploration, C target belong to P target, and third CS and C target are adjacent. Then we take the initial solution theta in it, maybe it could be 3, it could be anything from CS, and use reproducibility improvement to optimize its fitness and its probability to fall into C target. Now we are moving this particular solution from CS to C target. In the end, we collect the solution resulting from optimization process known as theta togo. But in this whole paper, they say that it's not 100% sure that you're going to get this theta togo. You can, like, nothing prevents the mean descriptor of the optimized solution theta togo for not being in the target cell. This can happen if the descriptor cell is not reachable or reproducible mechanism ends too early. So it's not 100% sure that you're going to get into that particular box or the adjacent cell that you're trying to explore. But if you get, then you will get a solution that is as par as your current solution or even better than that. So we add C target to the set of explored set P exploration and remove from P target. I explained to you the P reproducibility improvement mechanism already. So let's go back to our ARIA. So what ARIA here does is that it says that you have an archive of solution, right? A quality diverse algorithm or evolutionary feature search or hyperparameter optimization algorithm, right? It produces a set of solution. You map the solution into 2D map, right? And you find out you're going to optimize or reproduce this particular cell. So this is the archive, where it is. Let me show you. Archive completion phase. And first is reproducibility improvement phase. So now what it's going to do is that it will select a set of genotype by evolutionary search or quality diverse algorithm theta. Number of gradient step, n grad, number of samples per gradient, ns, standard deviation sample. And now it's going to select P exploration, P target, all the cells partitioning the descriptor space. Now reproducibility improvement phase. For each genotype that belongs to this particular algorithm that the archives have produced, something like that, it's going to evaluate genotype ns time and collect the descriptors. Cj is the mean that this descriptor cell belongs to. Then it produces the reproducibility improvement algorithm that will return theta j. Cj is already, we have the mean descriptor. We add Cj, P exploration, and remove from P target. Now, while P target is not empty, we are going to select two adjacent cell, CS that belongs to P exploration, C target that belongs to P target. Theta is genotype associated with CS. Theta target will come from reproducibility improvement algorithm. We're going to add this theta target to the C target to P exploration, remove from P target. So generally, what happens that archive solution is there. This particular adjacent cell is selected. We are going to take this genotype and we are going to find what solution can lie into the adjacent cell that can reproduce the current solution, even get better than them, in my opinion. So it reproducibility improvement mechanism happens. Generally, this solution that is sampled here, sometimes they are ranked by fitness or ranked by closeness. If it's inside the cell, there's the stochastic descriptor of sample solution. That is the particular theta that we are going to get from gradient Gaussian distribution. If it's ranked by fitness, it must be inside this particular function. And if it's outside this particular box that we are seeing, the descriptor space, it is ranked by closeness to the center of this particular box. After that, we estimate the theta and we run reproducibility improvement mechanism as much as we want for that particular gradient step. At the end, we'll get a new genotype that will fill that particular cell. So what I understood from this paper is that it exploring the space that we cannot even think or explore it in a different way with using its whole gradient step or gradient ascent in this mechanism. And reproducibility improvement mechanism tends not to degrade the solution as much as I've been said in this paper. It doesn't degrade the performance. It's on par or it's increase the performance. So maybe it could be used better in searching new search space in hyperparameter optimization algorithms, things like that. But it's a simple algorithm. Let me see. Let me explain and see the matrix or things like that, what it's going to correspond. So if we go here, QD algorithm, matrix. So matrix. So it uses very different matrix. First is expected fitness and correlated QD score. So if expected fitness is a matrix that characterize the average performance of a solution with respect to a given task to estimate EF of a single solution. Solution is reevaluated multiple times denoted as M, and the fitness value obtained from this evaluation are average. So simple, it's a mean, right? And QD score is sum of all the expected fitness solution contained within the archive. So this is the expected fitness, and for corrected QD score, yeah, it's all correspond to sum of all the expected fitness. Then we have negative descriptor variance NDV and variance score. So generally it says that probability of belonging to the mean descriptor cell provides insight into how constant a solution decrypts in terms of ending up in a cell. And variance score is generally sum of the normalized NDV score for each cells in the archive. And other than that, it also uses probability of belonging to mean descriptor cell and probability score. So it generally means that probability that descriptor of a solution belongs to designated cell, and it has all the formula that we can use to decrypt it. I don't think so generally useful right now. It was useful for this paper, but not useful for us right now. P score equals to the sum of probability obtained value from this solution in the final archive. Then we have archive profiles. Generally, it changes the corrected archive solution to this particular criteria. And then corrected archives. The archives returned by QD algorithm may contain degenerate solution whose descriptor is significantly different from expected descriptor. Generally, they explain corrected archives so that they can compare like map-alike solutions with the current solution that we have. So the cell a solution is placed may not be the cell of the expected descriptors. So we designate those archives as illusionary archives. To elevate this issue, our results are presented in the corrected archives 11, 12, 21. Given an archive for set of genotypes returned by QD algorithm, all genotypes are reevaluated n times and placed in new archives called corrected archives based on their mean descriptor, generally what we had explained so far in this algorithm. They only keep the solution having the best expected fitness. The main difference between illusionary archives and a corrected archives is described in figure 2. If we go to figure 2 here, you can see this is the illusory archives. Then this is the corrected archives. Then this is the ARIA archives that we have seen. And other than that, I have explained ARIA, I have explained these things. Corrected archive explained. So yeah, there are 3 variants of the ARIA. First is ME init. It takes an input of archive returned by map elites. PJ init takes an input archives and returned by PGME. This is a whole different algorithm. So it takes an input from that particular custom algorithm. ES inits, as name suggests, evolutionary strategy algorithm to maximize the performance of a single solution. So yeah, first baseline, they considered comparison with ARIA is the map elites, which samples only one descriptor and fitness per solution. It says that it samples for the map SE, that is MESA. It samples several fitness and descriptor and use them to calculate the mean fitness and mean descriptor. Then we have map elite sampling and reproducibility consideration. Here, the fitness of each solution is modified to take into account the reproducibility problem. Then we have other algorithms too. Then the task, what the particular task is about. I think instead of explaining, you can show you what the task is all about. Let me see. I think it's visible now, right? So generally what they are trying to do is that don't bet on like alone. Yeah, simple. So they use 3 tasks. Anti-omnidirectional task. Generally, it's a robot that goes into different directions. You have to estimate as perform. I'll explain it to you more, but a visualization is something like this. You can see evaluation 1, evaluation 2, evaluation 3. So run evaluation 3 times, and all the 3 times the robot trajectory or final destination is extremely different. As you can see, evaluation first, it's going straight, coming to this particular direction. Here it's going towards right. Here it's going towards right, then coming down straight. But when they optimize it by ARIA, evaluation 1, evaluation 2, evaluation 3 becomes constant. As you can see, all the 3 robots are working in the same direction. So it's one of that. This is for like omnidirection. That is, there are 4 hands for this particular robot and works in all directions. Then they have walker 2D unidirectional tasks. Generally, it goes into one direction. So here you can see, same as I've explained earlier, evaluation 1, evaluation 2, evaluation 3 are totally different. Then optimized by ARIA. All 3 becomes constant. Not evaluation 2. Evaluation 2 sometimes it's a little bit different, but yeah. Then after that, PGME, same results as ARIA still, and it is the same result. So generally, noise aid deform arm. The arm task consists of planar robotic arm that we control different final position. The first one which I showed you, that was like a spider. So it says that it considers angular position and successive actuators. The fitness promotes solution having homogeneous set of angles. Some Gaussian I added to make the evolution uncertain. So anti-omnidirectional is finding high dimensional controller, brings 4-legged robot in a diverse final position. Task fitness equals to a non-discounted sum of rewards over an entire episode. It also rewards promote solutions which don't die prematurely, and it penalizes the high energy consumption because it's a space robot type of thing. And walker unidirectional tasks find diverse way to move forward as fast as possible. Descriptor here characterizes the proportion of the time each leg touches the ground. But yeah, it's simple. And then is all are the implementation details of this whole algorithm. Let me see. Implementation details, where we have descriptor space. They generally define all the things that they're going to use. I don't think so. That's much more explainable here because they use different gradient, different solution for different things. And in the end, in the results, I will just say it says that ARIA increases the coverage of the corrected archive by 50% by all tasks. It goes into different scenarios and results like mean intervenant, which relies on better corrected archives, things like that. And things that make much more sense to go into the results. But yeah, in the discussion, it just says that it requires a high number of evolution. That makes sense. And it's only the limitation of this particular algorithm. It also says that cells are selected in archive completion phase could not be improved. For now, cells are selected without taking into account their solution performance or reproducibility. Yeah, like currently we are just taking the adjacent cell. Maybe this cell could be compared with the mean cell or things like that, or any other cell that could be empty would be much more useful than going for the adjacent cell. But that's the simple explanation of this whole paper. I tried to keep it a little bit brief. I don't know. But yeah, my idea is to use this reproducibility improvement mechanism to diverge the solution of hyperparameters, or maybe optimize that hyperparameter towards that global minima, things like that. But yeah, that's it. Yes. Thank you.
Thanks, Aaryan. Nice presentation. Does anyone have any comments or questions for Aaryan?
So let's start, right? So hi, Aaryan. First of all, I didn't understand the archive. It's kind of
archives. It's simple, man. This archive of solutions is just like to say, for feature selection, we produce a lot of solutions, right? Number of features, like something like that. So archives is just the set of solutions that is produced in one generations or things like that, and they map it into a 2D space, describing its novelty. Novelty is given a number and just mapped into a 2D space. That's what I understood in this archive.
So we are going to create like a 2D image, just because that was in the paper. So let's keep with that idea. So we are going to create a 2D image there, which we have columns, like blocks, divide them in blocks. In each block, we have solutions that are close to each other. And the main objective is that the variance should be minimum in that block. So the solution should be close.
It should be very close. It should be very close. Solution should be very close.
So we can say that in that block, there is not a lot of novelty, right? Because if the solutions are close, there is not a lot of novelty on that
maybe.
Block.
If this is there, but yeah, they also say that the solution which are producing is the best one in that particular block.
Yeah, yeah. It say that, but okay. But the thing is, if there is not any in the end, he will only keep the best solution for each
Yeah,
block.
best solution for each block, something like that.
Yeah. Okay. So now related to the neighbor of a block, what it's been done is like we have a solution of a block, and then we are going to, from that solution, we are going to try to go to the another to the adjacent I don't know how to the neighbor block.
Adjacent block. Yeah, adjacent block.
So how that is done? We are going it perform like mutations until we are going to
Kind
the
of.
other block.
Yeah, kind of. You're producing mutation, right? Let's just say mutation. Simple mutation. What is simple mutation, right? We have number 5. We add number 1 to it, so 5 becomes 6, something like that. So it's using a gradient ascent type of step by calculating some random value from Gaussian distribution taken from there, and using this whole equation to form that particular theta in it, something like that. That's what I showed. And let me see, find it here quickly. I don't know. Let me share my screen. Entire screen. Just a second. Share. Come on. Can you see my screen? Yeah. So it's something like this. So theta in it is 3. We have, this is a random value C target, like number of gradient. Let's just say I'm doing 1, ns is equal to 3. So this is the Gaussian distribution value randomly selected to the mean. It says that mean should be 0. So that's why I selected 0.3, 0.05, 0.02. So it could be very close to 0 type of thing. Then fitness value 879, just a random value. Descriptor, that is the novelty score that they give, super random. So what I do is that I calculate it using this Vj multiplying into the standard deviation that we have and theta in it, temp in, and generally we calculate this. I forgot this name, G something like that. So it's using this equation. 1, 2, 3 represent the rank. V0, V1, V2 represent that standard Gaussian distribution values. 1 by standard deviation and simple GE. Then we add GE to our initial value theta in it. And then they try, if I do it the way that it's defined in the algorithm, so number of gradient is equal to 3, ns is equal to 3, things like that. It starts from 3, it ends around 8.72. This is super random, but yeah, maybe doing the fitness and all other things, this rank would change, things like that. Maybe it could be different.
Okay, so let's see. The archive, because you say that is not the best using the neighbor, the current block to create the neighbor, because maybe on the middle of that image that we are talking about could create a better solution. I don't understand that part. Can
maybe let's see. This is the adjacent cell they're saying, right? In the end of the paper. Went too deep. So in the end of the paper, they say that also the way cells are selected in the archive completion phase could not be improved. For now, cells are selected without taking into account their solution performance or reproducibility. That's what I was thinking. We are selecting the adjacent cell right now, right? Maybe this yellow cell that is in between is empty, right? So maybe this cell should go here. Maybe here the solution lies. Let's say this is empty. So currently it will select this by this whole reproducibility improvement mechanism, stuff like that. Maybe if the solution lies here, how we are going to go here, something like that.
Yeah, but the archive there is an order on the archive in the way that the solutions are put. Yeah,
maybe
there's an order.
If the descriptor calculation has some order in calculation, so maybe it exists. If it doesn't, then I don't think so. There's an order. Maybe if you're calculating for HP, I don't think so. There's an order of things like that.
So not necessary. We need to go to the neighbor of this block.
Yeah, maybe not. Maybe yes, maybe not.
Yeah, and maybe we can like not only use one block, but we can combine like this the lower one with the upper one. So now we're going to use 2 blocks to create the new adjacent one.
Yeah.
And then we can maybe explore better, because then we can be exploring the upper left and the lower right at the same time. So we can like kind of enhance the velocity of the conversions for this to create these two blocks.
Yeah,
So
depends how we are going to calculate it. That's the only issue. We have to go for very simple calculations, not use the proper fitness function, things like that.
yeah,
But
because
yeah, as you're saying,
if you stop to think, we have two best solutions on the upper left, not two best solutions in these two blocks, because each block has one best solution one. So if you get the first block and then you get another block, and then we are going to combine them. So now we are not exploring the adjacent, but now we're going to combine. So we have a new solution, and then we can, this new solution is a combination of two of them. So now we can explore all the left one or the right one, or any other space of these archival solutions.
yeah,
So maybe not be stuck looking at only one block, but maybe take the neighbor of this block that you don't know yet, and use this neighbor to try to compute this new one.
yeah, totally agreeing there. I'm totally against this adjacent one. I don't think so. It makes sense if we are doing for broad term.
I think
But I
it's
think
possible. I don't, because the outside we are using, he used rank by closeness, right? So I think
rank
it's
by
complete.
closeness to the other centroid of this block.
Yeah, I think it's completely possible if you don't consider one block, but you consider a set of blocks. I think it's possible to do that. But I don't know. You have to try it. It's pretty interesting. Interesting. I don't know how to pronounce that, but yeah, maybe. I don't know. I don't know. I have to take a look again.
Yeah, it's an interesting paper, right?
Yeah, I can see applications for it.
Yeah, that's why I selected it.
But the main idea, they have an archive of the best solutions. It's something that's pretty interesting, because now you can, because before we just kept the best solutions, right? We have a list and we kept the best solutions.
Yep.
Now we have several types of solutions that may or may not be connected to each other. So we have a lot of things that we can choose. There has some high difference between each other, right? So
we'll have some novel populations and how we select it. Now we converge towards a solution. These whole three things can change a lot by this simple algorithms, and even changing the adjacent cell formulation, things like that. That was my particular idea with this algorithm.
Yeah, the noise on the outside, where would it be? We have
for
like
us
on the date. Yeah,
it will be simply in the fitness function, or maybe the mutation functions values that we use, right? Maybe I'm talking about AFS, like maybe some mutation function values could be the issue.
It will be coming from the data, or we are going to insert noise there?
For both, from the data. I won't say data. Yeah, if we trace it back, it would be data only, but I was thinking fitness function and one or two from the mutation function values, like how much are we going to mutate it, things like that, because we have some values, right?
I see.
So these two. But let's see. I think first application will be in hyperparameter optimization, but let's see.
Yeah. No. Yeah. Pretty good paper. Yeah. I'm interested. So yeah. That is all my question.
Nice. Anyone else has any questions or comments for Aaryan?